Well, the focus of this video is to delve into voltaic cells and to calculate standard cell potentials and Gibbs free energy of those voltaic cells. Now that you've completed that POGL activity on batteries, you should be familiar with these terms that you see off to the side here and with the basics of how a voltaic cell work. If any of these terms don't look familiar to you or you don't know how to define them, please go back to that POGL, find those terms and review that material. Here's a couple of memory devices I just find really helpful. So if any of them work for you, be sure to use them. I think you're already familiar with red cat and ox. The reduction takes place at the cathode and oxidation takes place at the anode. You can also use this vowels together, anode, oxidation, consonants together, cathode reduction. Here's one more. Electrons move away from the anode and closer to the cathode. Standard cell potential is also called the electromotive force or cell voltage. It's the potential difference between the anode and the cathode in a voltaic cell. When one of the electrodes is hydrogen gas in a solution of hydrogen ions with a piece of inert platinum metal that acts as a surface for the hydrogen gas and ions to meet, it's called a reference electrode. Hydrogen ions are universally assigned a reduction potential of 0. So, if a positive value appears on a voltmeter as you see here, that means that copper plus 2 has a higher reduction potential than hydrogen ions. And electrons are traveling from the hydrogen gas through the copper strip to the copper plus 2 ions in solution. Copper is then the cathode because it's the site of reduction. A negative voltage, on the other hand, would mean that hydrogen is acting as a cathode and the other cell would have a lower reduction potential than hydrogen. When we test these cells under standard conditions, we get the values on the standard reduction potential chart. Okay, so we need to be able to use that standard reduction potentials reference chart to calculate the standard cell potential for a voltaic cell in which hydrogen is not one of the electrodes. So here's an example problem. Calculate the standard cell potential produced by a voltaic cell consisting of a nickel electrode in contact with a solution of nickel plus 2 ions and a silver electrode in contact with a solution of silver ions. So first, we'll write the two half reactions. Okay, I've written them here. Notice that I wrote them both as reductions. Now we'll go to the standard reduction potentials of half cells reference sheet and check out what those half cell potentials are. I've underlined them here. Notice that the silver ion has a higher reduction potential, so the silver ion will be reduced and the nickel electrode will be oxidized. All right, so the cathode will be the silver and the anode will be the nickel because the silver has the higher reduction potential. So when we fill out the formula, we get a cell standard is equal to the reduction potential at the cathode plus 0.80 minus negative 0.26 volts for the anode. And that gives us a sum total of 1.06 volts. That is our answer. One way to determine if a voltaic cell will be spontaneous is to calculate Gibbs free energy. It's a measure of the spontaneity of a process that occurs at 25 degrees Celsius in 1 atmosphere. If our standard Gibbs free energy is negative, the reaction will be spontaneous. So to determine Gibbs free energy, we'll use this equation, where N is the number of electrons transferred in a balanced redox reaction. F is the Faraday constant. It's 96,485 coulombs per mole of electrons. This is basically the quantity of electrical charge on a mole of electrons. And E is the standard cell potential of a cell. These units of Gibbs free energy will be in joules per mole, but we usually express them in kilojoules per mole, so we'll be converting. This example problem says calculate the Gibbs free energy for that nickel-silver voltaic cell that we just looked at in example 1, and express the answer in kilojoules per mole with 3 significant figures. So before we can go ahead, we need to figure out how many electrons are transferred when this redox reaction is balanced. What I've done is written the nickel as an oxidation and the silver as a reduction as if I was going to balance this equation, and I noticed that everything's balanced except for the electrons, so I'm going to have to double this silver reduction. So now we know that were we to balance this equation, 2 electrons would be transferred. Okay, I filled in the values for the Gibbs free energy equation. So I've got -2, that's the number of electrons transferred. I've got Faraday's constant, and I've got the value for the voltage across that cell that we figured out in the last problem. So if I put this in my calculator, I get an answer of -204,548.2 joules per mole. But we want this in kilojoules per mole, so I need to divide that by 1,000. If I move the decimal over 3 times and give myself 3 significant digits, notice this 4 is going to round up to a 5. So the answer would be -205 kilojoules per mole. Because this delta G is negative, this reaction is spontaneous. This problem is really going to pull everything together, so I'll show you how it works. The first thing I would do is look up the standard reduction potentials for these 2 ions. So I'll do that and write them down. So we can see that the sodium has a much lower standard reduction potential than the iron does. That means that the iron will be reduced, and therefore the iron will be the cathode and the sodium will be the anode. So I'll write the half reactions for both the oxidation and reduction. You can see here the sodium's been written as an oxidation, it's losing electrons, and the iron +2 is written as a reduction, it's gaining electrons. Now in terms of the plus or minus here, by convention, the anode is considered, for a voltaic cell, negative because it's the metal that's losing electrons. And the cathode is considered to be positive in a voltaic cell because it's where the electrons are flowing to. Now notice off to the right, what I've done is written the sodium as the anode with sodium ions in solution, and iron as the cathode with iron in solution. The salt bridge is connecting the 2 half cells together, and the electrons will flow from the anode to the cathode. Now when we balance this redox reaction, notice that we're going to have to double up on the sodium. So if I doubled up on the sodium and I added those 2 half reactions together, the electrons will cancel, and I'll end up with 2Na plus Fe plus 2 yields 2Na plus Fe. That's the balanced redox reaction. To calculate the standard cell potential for this cell, we will take the standard cell potential for the reaction at the cathode, that would be -0.45 volts, minus the standard reduction potential for the sodium ion, which is -2.71 volts. So when we do that math, we end up with a standard cell potential of 2.26 6 volts. Now we're going to calculate delta G. So delta G is -2 because we've got 2 electrons being transferred, times Faraday's constant, 96,485 coulombs per mole, times the standard cell potential, which is positive 2.26 volts. And we'll divide that whole thing by 1,000 because we want our answer in kilojoules per mole to 3 significant digits. And when we do that math, we end up with -436 kilojoules per mole. So that is a great summary of this whole lesson.